And let me know if you got to the point. The point was that the diagonal matrices work out really nice, and the other one does not work out nice. Matrix multiplication is actually a bad thing for computers. Who's a double major in here? Somebody's a double major in computer science now. I've always had one every semester. Yeah, it's bad. Like you don't want to do, if you have a huge matrix and you do matrix multiplication, it's like not ineffective. So even there, it's easier to find the eigenvalues and expand the matrix. Eric, I thought you should be like a double major in computer science and math.
I sometimes think I would like to have, but I also don't think I feel like I should just stay undergrad even longer.
I wish I could do it. This time I've studied.
I know.
Like do it over my study.
It's already been like 7 years.
All right, so the point of this is, you should have got the point, which was that if I have a matrix and I can expand it like this, then if I square this thing, so I'm just going to just square, then I'm going to show you for like if I take the nth power, because if you're going to plug it into a Taylor series, you have to find the nth power of this matrix, and you don't want to do that by multiplying matrices out. That's not good. It's unhappy. Well, you could probably give it to a linear algebra class if you're mad at them. So take the 50th power of this matrix and have it done by the end of the period without a computer. So here's the point. So if I have a squared, that's a squared, right? If I can expand it this way. And if I expand it this way, well, that means this. Do it twice, like so, correct? And then associative property thankfully holds, so we can actually lift off those parentheses. So, and then again, what's this guy right here in the center? It's an I. Some of your linear algebra class might say it's 1. They say 1 just it's I, it's the matrix. And then I times anything as itself, so this guy just becomes C D squared C inverse, and that you can calculate, right? So the same thing's true if I have A to the n, I'm going to have C D C inverse to the n, and the same thing will happen. You'll get a bunch of i's in the center, and you're going to end up with just C D to the n C inverse. So bring that power series on. If I have a diagonalized matrix, all I have to do is find the eigenvalues and I can stick them in there and take D, and I just have to do the C, D to the N, C inverse. Kind of. It's a little bit harder than that. So if I have E to the TA, like this, and I know that it's this power series, so I have all these guys. Like copy it before I move on. So I'm not writing out the expansion every time. So I have this power series, I plug this thing into there. I can take the nth power to each one of these guys. Haven't caught up? We have closed laptops, so it's just too distracting. All right, so now what do I do with this? Well, let me just pull the nth term. I'm deviating a little bit from my notes. My nth term looks like this. let me pull the t to the n inside. So if I have a t to the n on the outside, factorial out here, lambda 1 to the n, lambda 2 to the n out here, 0 is here. That, if I pull that t in, I have real n of 1 over, I can put scalars inside component y, so I get this. Like that. That's another hash mark that shouldn't be there. That's the nth term, looks like that. I can add, totally legit to add matrices, so I can add the matrices up. Let me do this in one piece because I just think you're going to write like till you have a cramp in your hands. The C's are all on the left. I'm allowed to factor the left. What I'm not allowed to do with matrices, I'm not allowed to let them commute. Like depending on who you had as your professor, who do you guys have? Ryan Allaire? Currently, Ryan, you have, yeah, he's probably going to say make a big hairy deal about it and it can't commute, and so you can't do certain things, you know. So you have to factor to the right and left. You can't rotate these C's and C inverses around. That's all you have to be careful of. But every left term has a C on it, and every right term has a C inverse on it. So I can just factor out the C to the left and factor out the C inverse to the right. And on the inside, what I'm going to get is 1 plus t, lambda 1 plus t squared, lambda 2 squared over 2 factorial, blah, 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 0, 0, 1 plus t, lambda 1, lambda 2, blah, blah, blah. What is this the series for? This is just like a power series from when you were little, when you first saw it. That's right. So this thing is really C e to the lambda 1 t 0, 0, e to the lambda 2 t. C inverse. Pretty damn cool.
You still have a C inverse on the left side of the board on that last row.
Oh yeah, yeah.
Right.
Thanks. So actually, I think the page of calculations going through this, like I did everything for my notes. If you actually want to see that, I'll just take a picture and send it if you want to see all the details in between. But really, like I split out the nth term so you can see what the nth term looks like, and then I'm just adding all the inside matrices, and that leads me to this with a C on your right, my right, your left, and a C inverse on my left, your right. And that's where you get your solutions have lambda 1s and lambda 2s. That's where it comes from. A little bit more on this. So how do they get the solutions to look a certain way? I'm not going to do all these calculations either. It's kind of totally good. As a math major, you have to be able to do two things. You have to be patient and be able to prove things. And you also have to be able to be patient and compute things. That's like part of like, sometimes we had students that in the math ed program that didn't want to do either. Like, you're going to have a hard life. Those are the two things we're supposed to do. Compute with patience and prove things with patience. So if I have a solution, see how I can do this without doing a bunch of. If I have a solution and it has a C and a C inverse on it, well, if it's a 2 by 2, I can actually write down what the inverse is, right? I could say, let's say C was A, B, C, D, right? Let's just say it was something like that. Then C inverse is going to be 1 over the determinant, and swap these two and put minus signs on these two. You learned that, I think, in the beginning of linear algebra, you learned that this is the inverse of a 2 by 2. And then somebody will show you the 3 by 3 is not so easy, right? But for a 2 by 2, it looks like this. If you put this inside this calculation right here, and you have it all as, maybe I'll put the notes out there so you can actually see all the calculations. You can also stick this in MATLAB or Mathematica and tell it to do it symbolically. What you're going to get at the very end, so if you put A, B, C, D in there and actually run it through a machine, what you're going to get is you're going to get play the Rocky theme song, and then you get something that looks like C1 e to the lambda 1t plus C2 e to the lambda 2t, K1 e to the lambda 1t plus K2 e to the lambda 2t. You'll get something like this. After you do all the matrix multiplications, and you multiply this also by an initial condition, you're going to get a 2 by 1 answer, right? Because you have a 2 by 2 matrix times a 2 by 1 vector, you're going to get a 2 by 1 answer, and this 2 by 1 answer is going to be this thing. Well, you can do some more shenanigans here. You can pull this out like this. Dr. Aleric's probably doing stuff like this in class all the time. You can do that. Right? You can split this off. So you can take out this part here and then sum it to this part here. Factor out e to the lambda 1 on the first component, you'll get this. Factor out e to the lambda 2 on the second component, you'll get this. That's the general solution. This is C inverse, yes. This one?
The far right.
This one is like so let me back up a little bit.
Very far.
This one?
Our general solution.
This one here?
The general solution. All the way to the right is the chalkboard. The second vector has something in the top right. Is that an inverse?
No.
Okay.
It's like leftovers. In your book, they should have something like this. They should have something that looks like x of t is equal to e to the lambda 1t times c1 plus e to the lambda 2t times c2. They should have something like that, where c1 is this vector here and c2 is this vector here. That's a general solution. Magically comes about from just knowing the eigenvalues and eigenvectors. I used to have a colleague in grad school always tell me, if you know the eigenvalues, you know everything.
So at this point, we've been seeing the coefficients for our terms as scalars as opposed to so why do we now have vectors?
Because you're working with systems of equations. equations. 7.1 starts with systems of equations. You've already kind of worked with systems of equations, right? I made you do it earlier, right? And if you have something that's not linear, guess what we do? We linearize it, and we look at locally around, and it becomes this again. So this is really what you need. We have 7.1 is about systems of equations.
So in this case, we would have multiple equations.
Yes, you have an x1 component, x2 component, x3. So if you have a system, think of like the Lorenzo tractor. It's a three-dimensional system. You have three what we call state variables, and each one of them describes something about the weather. So each one of them is going to have its own solution. X1 of t would be the first component. X2 of t would be the second. One of the easiest ones, I think you might have got these in Jedi math, where they have susceptibles and infectives. You might have even got that in 103, because it's an easy one to understand. You have two things interacting with each other. People are susceptible to the disease, and people are infected with the disease. And if they interact, there's going to be a dynamic that changes. The number of susceptibles are going to be pulled into the infected category, and if the infected recover, then they're going to be pulled back into, they can get it again, they can get pulled back into the susceptible. So there's movement between one box and the other. So each box has its own differential equation. So it's a system. You have two. And you might only care about one of them, like maybe the infecteds only. So you want a graph of just the infected, the second component only. Those are the graphs that you saw during COVID.
I guess we had system equations previously, but just not all of them.
Yes, so I think your book is trying to give you a refresher for linear algebra. And I gave you a little bit in the in-class assignment. And I think I also gave you some on homework. So I'm going to pass out your homework in a second. And then the classic tank problems. So that's the second part of your, I'm just going to show you how to do one in class. Tank problems, you may have seen that in, my son said he saw it in Jedi math. So you have two tanks with different concentrations of salt in them. There's water with a concentration of salt coming into the tank. There's water coming out of one tank and going into the other. There's water coming from the second tank to the first. Does it ring a bell? What he said is, I hate those problems. Like, okay, they're awful. But I was tortured with them, so I'm going to torture you back. I'm going to do what was done to me. So I gave you a tank problem. I didn't want to skip that. It would probably be more interesting looking at something like a COVID model. Carl Clark and I have a COVID model. I can show you that one as a real example. Okay, so let me finish up here. So your general solution looks like this. You're going to have to bind basically the eigenvalues every single time. This is why you're doing it. This is why you're finding the eigenvalues and doing all this stuff. I'll give you one open problem, and then on Friday's class we'll do the tank. Real quick, what was tank? So if you did the algebra and you actually multiplied all of these, you're going to get a whole bunch of constants, and those constants combine up to just be one number. So, and I'll put that online for you guys. I just don't want to write all that on the board. So if you do this calculation here with A, B, C, D as your C.
So it will be something that comes from our matrix that we
Yes,
have.
after you do the math, yeah. All right, so why is this all important? Well, you can break things down. And if you have something nonlinear, you can make something like a multivariate tangent line and look right around an equilibrium and ask what happens. So you're back to this linear equation. So what you're learning is actually super, super important because it works for everything. That's kind of how we handle things. But what if I had this? This is my open problem for you. What if this was a function of t? I want to kind of do the same thing I just did here. And so for every t, you're going to have different eigenvalues. It's going to be a function of t. But what allows you to do this kind of machinery is that it's the eigenvectors that make it allowable. So you really like those eigenvectors to be constant. So if I could do that, then I can do the same thing for this matrix that I did just now. I could do e to the a of t is the solution, but I need to be able to diagonalize. And to do that, I need constant eigenvectors. So I can get a c that's constant and a c inverse. All the math I just did for you only works if c and c inverse are constant. We've got the 2x2 case done for this to say what conditions have to be on the matrix in order for this thing to be have constant eigenvectors. 3x3 is wide open, like no one knows. So that's a pure math problem that's related to differential equations. All right, so let me pass out your homework. It looks worse than it really is. It looks like it's longer than it is. I walk you through my calculation I just did now,